Welcome back. This is the last part of the introduction series on neurotics. Here we will cover in detail how to save, how to export and how to share your networks. This will be done in real time so you can follow the steps. Let's assume you have created and tested your neural structure and you want to save it as a building block for a larger network. In the Editor tab on the bottom right section you can find the Save and Load buttons. This way you can store or load your networks as JSON files which can be used to reconstruct your networks at a later time. These are the structures you can share. Since these JSONs serve as building blocks, it's intended for you to be able to combine them. This is easy to do and there are two ways. The first way is for networks with up to 5 million neurons and is meant for fine structures and functional groups. Let's say you already have a neural network and you want to add something you've built before to combine it. Press the Import Subgraph button on the bottom right and choose the file. This is a very precise way to build networks because you have control over each and every position in this tab. As you can see, these graphs are disconnected from each other for now, but their initial connections are still intact. You can then combine them as you like, the traditional way, as you learned in the previous sections. For larger networks, however, with millions or billions of neurons, it's recommended to use the Fusion tool because it does not load the graphical representation of each and every neuron and thus is faster, with a little trade-off. If you have built your structures around the origin, you must know beforehand where your second neural structure has to be placed because it will keep the original positions and orientation unless told otherwise. Just above the purple merge button there is a field where you can set the distance of subgraph B on the right side in relation to subgraph A on the left side. You can load them with the blue and the pink buttons. The node representation above is just a visualization of what you already have connected. This will dynamically change when you create new connections. Every connection has a source and a target, like before. But this time you have to manually select the source node. You then choose which graphs, nodes and populations you want to connect to and choose your topology and synapse type, just like before. Previously set parameters, connections, devices, neuron types and positions stay intact. This way you can reuse building blocks, recombine them and test them. And here it should become obvious that this whole software is built to create a certain type of data structure. It's not meant to replace any software, it's meant to democratize neuroscience and make it accessible to everyone who wants to contribute or play around. For laymen, students and everyone who's interested. The software was developed around a data structure to create, combine and shape it. The data structure itself offers the organization behind the networks. Allow me to present to you the idea behind it all for 1 minute. Imagine having multiple people around the world working on reconstructing biological structures, each of them with their own substructures. The chance that someone finds something really interesting and shares it with the community becomes high, and even if not, the fact that someone actively learns about neuroscience is a good thing. You don't have to have a neurological degree or one in computer science to try it out. Make something that feels right for you. Maybe you are on the right track, maybe you are not, but finding out, that's research and humanity could greatly benefit from it. It's about understanding our brains and this is by no means an easy task. Working together on a bigger scale, no matter the background, becomes a necessity if we want to achieve this goal. For this, it was the most obvious decision to make the topology shareable in a single file to lower the barrier for this to be accomplished. Everyone with a computer can make discoveries now. Visualizing results is a crucial component of learning and comprehension. Historically, neuroscientific progress often relied on invasive experiments such as the seminal but ethically challenging studies by Hubel and Wiesel and others. Providing a cruelty-free platform for research with a low barrier for entry is, in my view, a necessary step forward. By participating in this digital approach, we can advance our understanding of the brain ethically, to a certain extent at least. Neurotics is a network builder, and at the end of the day, it's Nest that does the work. This is why you can be sure to use scientifically accurate neural models. What Neurotics does is it gives you access to Nest's full range of neuron models, which you can use in the application and outside of it, from simple integrate and fire to biophysically detailed Hodgkin-Huxley neurons with ion channel dynamics. While this covers cellular electrophysiology comprehensively, Nest itself operates at the network level and abstracts molecular signal cascades and subcellular biochemistry. The strength lies in simulating large-scale circuits and connectivity patterns. For more information about Nest, I would refer you to their website, which is linked down below. Here you can see how, through regional stimulation and some connections, we created an oscillation in the network. We can visualize the activity of every population as plots, but to get a bigger picture, it's recommended to take bigger simulation steps. You can pause the simulation at any time and increase the time steps Nest has to simulate before fetching the data. You can adjust this in the top left corner of the application. If you're wondering why some populations have two devices of the same kind, this has something to do with the way Neurotics works. For the live simulation, it attaches extra devices on your populations to be able to fetch the data for the visualization. These devices are temporary and are not safe with your network. They kind of replace your original devices for the run, but in the headless mode you will have only your original ones. This is the part that might interest researchers in this field the most. Since this is a research tool, it has to support headless operation. Rather than porting the entire application to clusters, Neurotics exports standalone Python scripts. They are completely independent of the main program. Since networks are saved in JSON format, these scripts can rebuild and simulate your networks on any system with Nest installed. They can be used as the base for further programming, which means you can construct your networks here and at the end of the script simply add your code. Make use of the graph structure and attach this to your main project, whatever it might be. At the end of the day, we are talking about a data structure that manages populations, and these are accessible at any time. A description of the data structure and how to use it will be available in the GitHub repository. To export a network for headless runs, you switch to the Editor tab and select the simulation view. It will provide you with information about your model distribution and give you the possibility to set the duration for your headless simulation, which can be altered in the script at any time. In summary, choose your simulation time, press export, and you'll be asked to select a location and a project name. After creation, navigate to that directory, activate your virtual environment and run the run.py script. That's it. Your network is now running independently. The gathered data by the attached devices will be dumped every 2000 milliseconds to your hard drive, but this is also adjustable in the script. It will be available in the same folder as the script. The nice thing is that you can use your own tools to analyze the data, since it's also in JSON format. But you can also use the built-in offline analysis in Neurotics. Just move or copy the data into the simulation history folder. Before we close, I want to mention Nest Desktop. If you have looked into Nest before, you've probably came across it. Nest Desktop is an excellent web-based graphical interface for Nest, developed by Sebastian Spreitzer and the Nest community. It's designed primarily for education. You can build networks in your browser, run simulation and analyze results, all without installing anything. It's a great tool, and if you're a student or teacher looking for a quick, accessible way into computational neuroscience, I would recommend checking it out. Neurotics is not a competitor to Nest Desktop. The two tools came from very different places and serve different purposes. Nest Desktop works with abstract circuit graphs. You connect populations and devices in a schematic view. Neurotics works spatially. Every neuron has a position in 3D space. Structures are shaped with polynomial vector fields and you see the actual geometry of your network. It's less of a simulation front end and more of a digital neuron microscope, a CAD tool for neural architectures. I didn't build Neurotics to compete with anything. I built it because I wanted a tool like this to exist, and it didn't. At that time, at least. It started as something I needed for my own work, a way to construct, visualize, and iterate on spatially organized neural structures without writing boilerplate code every time. And then it grew. The hope is that it helps others the way it helped me. If it does, then it was worth building. Anyway, this is the last video of this series. If you have watched the previous parts, then you are now ready to use this tool. Thanks for sticking to the end. Good luck and have a nice day.